this video, we want to determine the end behavior of polynomial functions. We want to be able to identify their zeros and multiplicities, and we want to be able to use that information to sketch the graph of a polynomial function. First, let's talk about what a polynomial function is. The general form of a polynomial function is going to look like this. Now, this looks very complicated, but it's really not that bad. Let's look at some concrete examples of what a polynomial looks like. With 4 different polynomial equations, notice that in all of these equations, I only have real coefficients. That means that the numbers you see in front of the x's are real numbers. They're not imaginary numbers. And notice that all of my exponents are positive and not fractions. Those are the conditions to be a polynomial. So here's an example of a 4th degree polynomial. We can see that both ends of this polynomial point upwards. We can see there's some places where this graph is crossing the x-axis, those x-intercepts there. And we can see there's a couple places where the graph changes from decreasing to increasing, and then changes again from decreasing to increasing there. Here's another example. This is a 3rd degree polynomial. We can see that this polynomial only has one x-intercept. You can see that the right side of this polynomial shoots up. As x gets really big, the graph continues to go up. And we can see that as x gets very small, to the left side of the graph, the y values shoot down. The y values go off to negative infinity. Here's another example of a polynomial. It's okay to have fraction coefficients. Fractions just can't be in the exponents. We can see that this is a 4th degree polynomial because I have an x squared here and an x here, which would give me x to the 3rd. Another x would give me x to the 4th. Both ends of this graph are shooting up. We can see that there's some places where this graph is crossing the x-axis at -5 and at 1, and that there's a point here at -3, 0 where the graph is not crossing but only touching the x-axis. And then here's another example of a polynomial function. This is a 4th degree polynomial, but now both ends of the graph point down. As x gets very small, the y's values get very negative, and over here on the right side of the graph, as x gets very big, the y values also get very negative. Here I can see 2 places where this graph is touching the x-axis. What I'm going to talk about with polynomial functions is end behavior. And end behavior is the fact that both ends of this graph point down, while both ends of this graph point up. Compared to, on this graph, the right end points up and the left end points down. And over here we have both ends pointing up. So what controls when the ends point up and when the ends point down? Really dependent on the leading term. And so what I mean by that, looking at this first example here, the leading term is x to the 4th. If I just look at the graph of x to the 4th, both ends of x to the 4th point up, and that's why both ends of that graph point up. Another example, if we look at this second one here, the leading term is 2x to the 3rd. If I look at the graph of 2x to the 3rd, it follows the same shape. The right end points up and the left end points down. So now we're going to go make a generalization about the end behavior of a polynomial based on its leading term. Generally speaking, end behavior is the direction that the function follows as x approaches positive infinity, which means as x gets very big, as off to the right of the graph, or as x approaches negative infinity, which means as x gets very small, off to the left of the graph. End behavior depends entirely on the leading term. The leading term is the term with the highest x. That we concern ourselves with is whether that exponent was even or odd. And depending on whether the exponent was even or odd, we go then look to see, well, was the exponent positive or negative? And depending on which of those 4 scenarios we end up with, even and positive, even and negative, odd and positive, odd and negative, that will determine what our end behavior will be. So let's look at an example. Looking at example 1, here I can see that the leading term is x to the 5th. In that leading term, the exponent is odd. It has an odd degree. and the leading coefficient is positive. So now that we know that we have an odd degree and a leading coefficient that is positive, I'm looking over here where the degree is odd and the leading coefficient is positive. When that's what's happening, the graph itself, the end behavior, will look a lot like x to the third, with an odd degree and a positive leading coefficient. So what our end behavior is as x goes off to positive infinity, as x goes off to the right, the graph goes up to positive infinity. It rises to the right. The graph goes up on the right side. Opposed to, as x goes off to negative infinity onto the left side of the graph is dropping down to negative infinity. The left side of that graph goes down to negative infinity. This is our answer for our end behavior. We are describing what happens as x gets very big and what happens as x gets very small. Let's do the same thing in example 2. But in example 2, we can't just look at the polynomial and explicitly see what the leading term is, because this polynomial comes to us in factored form. Because this is coming to us in factored form, instead of written expanded as that was, we first need to figure out what is the leading term. So if all of this were multiplied out, what would be the term with the highest exponent? We do not need to multiply all of this out. Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice. She is. Yeah, she is. Even times like when we work together, it's almost, I'm like, do you have a question about this part? Because like I can see she wants to ask something, but she doesn't. Yeah.
So that was it.
Yes, like, hey, perfect, here we are. Yeah. Thank you, Ms. Butler. Of course, quadratic. I see 3 factors. I see a negative 2, I see an x minus 5, and then I see an x plus 1 cubed. The leading term of this polynomial would include the negative 2. It would include the x from that second factor, and it would include the x cubed from the last factor. So if I were to multiply all of this out, the leading term would be negative 2x to the 4th. And what's important about that is that the 4 is even, and the negative 2 in front is negative. So we are dealing with a polynomial whose leading term has an even degree and is negative. So now I'm looking at the even side with negative leading coefficients. That's going to look a lot like negative x squared. Just thinking about what negative x squared itself looks like, because it's negative, it flipped over the x-axis. Because it was x squared, it is a parabola. Both sides of that graph are pointing down. So what we're going to do now is we're going to fill in these 2 blanks. What's happening as x gets really, really big, goes off to the right, and what is happening as x gets very, very small, as it goes off to the left to negative infinity? Well, as x goes off to the right, on the right side of the graph, the polynomial is going off to negative infinity. It is pointing down. As x goes off to the left, off to negative infinity, the polynomial is also dropping down to negative infinity. Well, we want to determine the zeros and their multiplicities. The zeros of a polynomial are the numbers of x in the domain that make the function equal 0. That is what these zeros are. They are the numbers that make the entire function equal to 0. So to find the zeros, I am going to set the function f of x equal to 0, and I am going to solve. Now to solve this equation, equal to 0, is very straightforward because it already comes to us in factored form. So because it already comes to us in factored form, we just need to take each of the factors and set each factor individually equal to 0. Solving the first equation, we can see that x is equal to 0. The second equation, we can drop the squared by square rooting both sides and see that x is equal to 1. And in the last equation, we can get rid of the cubed by cube rooting both sides and seeing that x is equal to negative 3. So the three numbers that will make this polynomial 0 when we plug them in are 0, 1, and negative 3. Notice that each three of those numbers, 0 coming from that factor there of 8x, 1 coming from this factor here of x minus 1 squared, and negative 3 coming from this factor here of x plus 3 cubed, each 0 corresponds with a factor. Each 0 corresponds with a factor. And in reality, for the x, I'm really just going to circle the x part because the 8 in the front doesn't really matter. Just as a quick demonstration, starting off setting this polynomial equal to 0, we could begin by dividing out by the 8 and notice that that does not change the zeros. So the 8 itself does not affect those zeros. Those coefficients in front of the polynomial will not challenge our zeros. So each 0 comes from one of these factors. Let's look at these factors closely to find their multiplicities. The multiplicities come from the degree of each factor, the exponent on each factor. So from the factor of x, there's an exponent of 1 there, so the multiplicity of 0 is 1. The factor that gave us 1 as a 0 is the x minus 1 squared, which shows up twice, so it has a multiplicity of 2. And the factor that gave us negative 3 has an exponent of 3, and so the multiplicity is 3. So we have found the zeros, and we have also found their multiplicities. In example 5, we want to do the same thing. We want to find the zeros and the multiplicities. I'm going to start off the same way we did in the previous example and set the entire function g of x equal to 0. That's what zeros are. They are the numbers that when we plug them in, we would get 0 out. To solve this, I'm going to set each factor equal to 0. The first equation is already solved. The second equation is solved by adding 1 to both sides and getting that x is equal to 1. And the last equation is solved by subtracting 3 from both sides and getting that x is equal to negative 3. So now that we have all of the zeros, let's go look at the multiplicities for those zeros. The multiplicities for those zeros depend on the exponents that we see on each one of the factors. But when we look at this, we don't see any exponents because each factor has an exponent of 1 on it. So I don't know why I wrote 3. Each one of these zeros then has a multiplicity of 1. Let's go in and look at the graph of this polynomial. It's given to us graphed here, and you'll notice that the place where this graph has its x-intercepts at the points -3, 0, 0, 0, and 1, 0, each one of those x-intercepts each correspond to one of our zeros. So in reality, x-intercepts and zeros are the same thing. The only difference is that x-intercepts are points and zeros are just numbers. Another word for zeros are the roots of a polynomial. About how x-intercepts and zeros are the same thing, and we see that illustrated here in example 5, where we have 3 zeros, each with a multiplicity of 1, so it's worth mentioning that each of their multiplicity is odd, and we can see the 3 places where these 3 zeros cross the x-axis on this graph. Here it is crossing at -3, crossing at 0, and then crossing again at 1. In Desmos off to the left here, I have graphed our first example, 8x times x minus 1 squared plus x plus 3 cubed. The graph is not as nice, but here is the graph here. Again, for each of our 3 zeros, we have a 0 of 0. We can see an x-intercept at 0, 0. We have a 0 of 1, and we can see an x-intercept at 1, 0. And then we have another 0 at -3, and we can see this last x-intercept here to the left. Notice that the ones that have an odd multiplicity, 0 and -3, the graph crosses through the x-axis at those points. But for the 0 at 1, where the graph has an even multiplicity, the graph does not cross through the x-axis. The graph simply comes down, touches the x-axis, and turns back up. But when the multiplicity was odd, like 1 and 3, which are odd numbers, at the 0 of 0, the graph crossed through the x-axis. And at the 0 of -3, the graph also crossed through the x-axis. And are summarized up here. When the multiplicity is odd, the graph will cross through the x-axis, and when the multiplicity is even, the graph will simply only touch the x-axis. So in example 8, we're going to start off by identifying the zeros. We would find the zeros by taking the polynomial and setting it equal to 0 and solve. Once we had it set equal to 0, we would set each individual factor equal to 0. I'll take the -3 here, but remember the -3 does not really matter. I get a 0 of 0. When we take the factor of x plus 4 and set it equal to 0, we get a 0 of -4. And when we take the factor of x minus 7 cubed and set it equal to 0, we can simply drop the cube by cube rooting both sides. We get a 0 of 7. The next thing we want to identify is whether the graph crosses or touches the x-axis at each one of those points, because we do know that each one of those gives us an x-intercept. So we do know that we do have an x-intercept at 0, 0. We have an x-intercept at the point -4, 0. And we have an x-intercept at the point 7, 0. Now, whether the graph will touch or cross the x-axis at those points depends on the multiplicity of those zeros. When we look at 0, it came from a factor that had an exponent of 2. So it has an even multiplicity, meaning that the graph will touch the x-axis at the point 0, 0. When we look at -4, it came from the factor of x plus 1 that had an exponent of 1 on it. 1 is an odd number, and so the graph is going to cross the x-axis at the x-intercept of -4, 0. And when we look at the 0 of 7, it came from a factor that had an exponent of 3, which is an odd number, and so the graph is going to cross the x-axis at the x-intercept of the 7, 0. In the graph where the function changes from increasing to decreasing, or vice versa, where the graph is changing from decreasing to increasing, so points that look like this, or points that look like this, so relative maxima and relative minima, the maximum number of turning points that a polynomial can have is 1 less than its degree. So if the degree is n, it can have at most n minus 1 turning points. So for example, in number 9, the degree of this polynomial is 3. So its max number of turning points, which would be the same number as the max number of relative extrema, would be 1 less than 3. And 3 minus 1 is equal to 2. So in other words, that graph is saying if you're dealing with a polynomial that has degree 3, it's going to look something like that. And 2 times is the most number of times. Now that we've seen all this information about polynomials, we want to use it all together to be able to graph a polynomial function. So let's look at example 10. We're going to start off by identifying the end behavior of this graph. The end behavior depends entirely on the leading term of this polynomial. This is not written out in expanded form. This is given to us in factored form. So to find the leading term, I'm going to look at each factor individually. I'm going to look at the factor of x minus 1 squared. I'm going to look at the factor of x plus 3. And I'm going to look at the factor of x minus 4. And I'm going to pull the highest degree of x out of each factor. In the first factor of x minus 1 squared, the highest term we would get is x squared. In the second factor of x plus 3, the highest term we would get is x. And in the last factor of x minus 4, the highest term we would get is x. Multiplying all of those together gives me a leading term of x to the 4th. The 4 is even, and that leading coefficient is positive. There's no minus sign out in front like there is here in example 11. So even and positive means that I'm expecting both ends of the graph to point up. So now we can say that as x goes off to positive infinity, the right side of the graph is pointing up to positive infinity. And as x goes off to negative infinity, the left side of the graph is pointing up to positive infinity. Now that we know the end behavior, and we found the leading term to find that, we can see that the degree of this polynomial is 4. That's the highest exponent that we would see if we multiplied it all out. The maximum number of turning points is 1 less than the degree. So the maximum is 4 minus 1. The max is 3. Now let's go on to find the intercepts. I'll start off by finding the y-intercept. We find the y-intercept by setting x equal to 0. So I'm going to plug 0 in for x. And I get out a negative 12. So our y-intercept is at the point 0, negative 12. I'll go ahead and plot that on the graph. About right there. Next, let's go on to find our x-intercepts. Remember that our x-intercepts are the same things as our zeros. We find x-intercepts by setting the entire function equal to 0. So if I were to take each one of my factors, if I were to take the factor of x minus 1 squared and set it equal to 0, and the factor of x plus 3 and set it equal to 0, and the factor of x minus 4 and set it equal to 0, we would get x equals a positive 1, x equals a negative 3, and x equals a positive 4. So we have x-intercepts at the points 1, 0, which I will plot here on the graph, negative 3, 0, which I will plot here, and 4, 0. So we have our x-intercepts plotted. Now let's go on to see whether they are touching or crossing. At the point 1, 0, it's going to depend on what the multiplicity of 1 was. The 0 of 1, the x-intercept of 1, came from the factor x minus 1 squared. It had even multiplicity, so this here has multiplicity 2. Because that is even, it is going to touch at the point 1, 0. The x-intercept of negative 3, 0 came from the factor of x plus 3 that has an exponent of 1 on it. So here we have multiplicity 1, which is odd. So at the point negative 3, 0, it's going to cross through the x-axis. Odd multiplicities will touch. The 0 of 4 had a multiplicity of 1. You can see this has an exponent of 1 on it, which is odd. So at the point 4, 0, the graph is going to cross the x-axis. So now let's use all of this information to come in and sketch this graph. I'm going to start off by looking at the end behavior, which tells me that the left side of this graph points up. So when I come in to start drawing my graph, I am going to come in with the left side of the graph pointing up. I am going to come down and approach the x-intercept at negative 3, 0, where I see I need to be crossing through the x-axis. So I'm going to cross through the x-axis there. I know I need to continue my graph to go and hit this y-intercept here at 0, negative 12. And then I need to go up to come hit the x-intercept at 1, 0, where it only touches the x-axis. That will come up, touch that x-intercept, and turn back around. Now notice that when you come up and touch the x-intercept, you should not come up and touch it like a corner, because polynomials are smooth. So you should come up, touch it, and turn like a curve. But then you have to turn again, because you have another x-intercept up here at the point 4, 0, where the graph is to cross the x-axis. So it crosses the x-axis and it continues going up forever, because we know that the right side of the graph also points up. So that is how we use all of that information to graph a polynomial function.